Do you know there was a bridge in Australia or Europe? I don't remember exactly. I think in Australia. There was a bridge in Australia collapsed due to radiation. Do you know that? Did you come across this news? In all our codes everywhere, so far in the global design, or you take any types of codes, design codes, we are considering the major types of loading like live load, dead loads, and then the lead load means self weight of the member, and then the wind load, lastly seismic load or earthquake load, right? These are the four types we usually consider for our design. But there was a failure of a collapse of a bridge due to radiation, effect of radiation. Right now, it sounds that you have to consider other type of loading, other type of failure, like this radiation due to radiation. We do not know whether radiation from the environment or radiation from the rocks, the isotopes beneath the ground. We do not know. We have to identify the where, but it was said in the news that due to radiation effects, the bridge got collapsed. So it says that it reflects on redesigning or considering the radiation types of failures or the type of loading that is causing failure in the members. So like this, you people are going to face many challenges in the future design. So you must do try at least few types of questions that we are giving you every class and that are there in the textbooks. Thoroughly work out, and if there's any question, you ask immediately. Right? I don't know much about this type of this news. If you have a chance, you please read about this information. Failure due to radiation effect, not only loading or seismic loading or wind load or other types. Right. Design a shaft to resist both bending and torsional moments. So all of you know that if there is any compression or tension, you have tension and bending. But the shear, the third type of failure, which is shear load, will cause automatically the torsion load or torsion moment. Okay, shear will cause torsion moment. Normal tensile and compression will cause or bending will cause bending moment. Okay, prismatic beam design. Prismatic, see the term itself prismatic. Prismatic means geometrically similar. Again, it's a symmetric member. Prismatic again, referring to a symmetric member. The cutting section at any plane will lead equal halves on both sides. We are going to find number one is a prismatic and axially loaded. Once you're thorough, you can modify the values, the lever arm, to find out the corresponding uh, non-prismatic section. Why we are not taking non-prismatic section into consideration? They're all non-linear. It is very difficult to model or analyze using the simple arithmetic methods or the static equation that we are using. You really have to go through for proper design. You really have to go through what do you call the matrix analysis using MATLAB or using software using StatPro and using softwares only. You can analyze thoroughly the failure pattern, the corresponding design will be appropriate. But when you do manually, you can only get approximate value. That is one thing. When you at your job place, you will be designing for non-linear and non-prismatic sections, right? That is quite common in every design. But by making use of the software, understanding the basics, the formula involved, by making use of the software, your complex problem will be conveniently analyzed and designed. Right. Let's understand thoroughly about prismatic beam first. A beam is designed based on the strength so that they can resist the internal shear and moment developed along their length. So bending is always along their length or along parallel to the longitudinal direction of the member. Although some beams may also be subjected to axial force, the effect of it is negligible compared to others. Ensure that the bending stress and shear stress do not exceed the allowable bending and shear strength. Okay, allowable means the material. In all cases, we are designing according to the material allowable things or material strength, not exceeding. Failure, there is no failure due to what do you call that? Factor of safety is good. Factor of safety is always maintained above 1. then you are designing for not exceeding the allowable bending. A bending design requires in beam section modulus, right? I over C is Y. Hence, using the Fletcher formula, sigma is equal to my over I. Later, I will change the notations. It is my over I. We can have the formula as section modulus equal to m over sigma. Mmax is determined from the moment diagram and sigma allowable is specified in a design code. When you choose a material, aluminum, alloy, or any type of material, iron, or any type of material you choose, it will give you the design value allowable or strength value, bending stress value from the code book. We will give you the value first in the exam, or I provide the table, attach the table together with the question paper to choose the value, unit stress value. Right. Prismatic section will be like this. Hot rolled steel sections are mostly used. The appendix A and B, I will show you. When you're all using the code book, the same code book, right? Ibler. If you see this appendix B, are you having it right now? Can you go and check? Otherwise, I will, at the end of this slide, I will show you the appendix B. We'll have all the section values. We will go once again to check, don't worry, because I brought the section already here. AISC, American Institute, have standards W460 times 68 is showing like this. Height is 459, okay. End to end height is 459, approximately 460, right? The small mm, right? Small mm that is missing, 1 mm missing will be due to the material, right? Sometimes they cannot get a very clear cut dimension. So around this value it will be designed, and the weight is equivalent to 0.68 kilonewton over meter. When I say 0.68 kilonewton over, you are able to imagine the value. Okay, come on. The flange looks like this. One moment. Flange look like this. Thickness of the flange is 15.4. Thickness of the web, this is called web. This portion is called web. This is called flange. Top flange, bottom flange. Thickness of the web is 9.14 mm. And the section, this is called section. What section means? You have to say like this, W460 times 68. Right. And one of the codes will have like this prismatic beam section. We'll have all the section word names, area, depth, web thickness. This is all manufactured. This is already manufactured, and if you're going to use it in your site, it will be supplied to the site, right, to the contractor. You will have different sections, and then you can choose based on your design values for adapting in your construction. Right. Prismatic beam section. You're going to design this one like this, right? Given the load, you will choose from here. Vice versa, given the load, you are asked to find the stress. A stress is given, and you will be asked to find the section modulus corresponding to the moment produced. Okay. Prismatic beam design. Wood sections are listed by National Forest Products Association for use in the design. Nominal dimensions in multiples of 25 mm or listed. Example 50 times 100 mm. Actual or trussed dimensions or smaller being 37.5 mm by 87.5. Dressed means clear surface. No, they want a white and smooth surface. They do some smoothing. What do I forgot the name? Filing. The filing. They do some filing at the side. End up with 37.5 and 87.5 mm. Reduce the section at the side. After loading, they will do filing to fix having a smooth section, uniform section, and for bright color, whatever the requirement of the site. By that, the value will be reduced due to filing. Just crush it, file it at the site to get this dimension. The reduction in dimension occurs in order to obtain a smooth surface from lumber that is rough sawn. Right? From although the manufacturer ends with this, manufacturer clearly in the beginning also see here 459, 460 turns to 459. Although they try to reach 460, they cannot reach 459. And coming to site, due to loading and unloading, transport, the lead time taken. Due to all this effect, there may be slight change to neutralize or to balance out throughout the section. They do filing at the side, end up with some section reduction at this point at the side before using. So you have to make this note. Obviously, actual dimensions are used in stress calculations. So you can use the actual one in stress calculation. You will be given, for now you will be given, but try to understand these variations that is happening, minor variations that is happening in the actual design and the manufactured one. Right. Prismatic beam design. Built-up sections is constructed from two or more parts joined together to form a single section. Right. And this is welded because welding, they put the welding, different types of welding. If it is welding, there is some material here, like a fillet, filling with some fillet. With that, this web is joined to two flanges. In this case, bolt and rivet, bolted. This is bolted with the you forgot this term. This one, fillet. I think fillet and the bolt. They use a fillet to connect both, and onto that, on top of the fillet, they put the bolts. Okay, on top of the bolt, they put the bolts. Bolts are connected. See, these two bolts are supporting the flange, the web, and this one supporting the flange and this web. Like this section may be either welded or bolted. Wooden hollow. Sometimes the member may be a hollow one, box type, hollow box, or filled type, gulam beam, right? Gulam beam. You see here the variations. It's all depending on the purpose and the design. One normal stress, if the beam is relatively long, it is designed by finding its section modulus using Fluxo formula. We have already seen this one. This and this also already seen. If roll seal sections are to be used, several possible values of S may be selected from the tables. Of these, choose the one having smallest cross-section area, since this beam has a least weight and is therefore the most economical one. Right. You can also test with the different values of sectional dimension. Go directly to the table. I will explain about the table later. It's not here. Right. You can also test and see by changing the sectional value, whichever is appropriate according to the bending moment and shear force diagram, shear force values that you are finding. You can change the dimensions, right? You can change the dimensions of the sectional value to suit the required bending moment, to support the required bending moment. Prismatic beam design. Make sure that S is slightly greater than S required. As usual, the factor of safety applies here, and the required should be more than the selected, right? Like what do you call it? The member should be good enough, or member should have more section value than the design one, so that arching moment created by the weight of the beam can be considered. Shear stress. Normally, beams that are short and carry large loads, especially those made of wood, are first designed to resist shear and then later checked against bending stress requirements. Using the shear formula, check to see that allowable shear stress is not exceeded. Allowable shear stress is not exceeded the designed one, which is tau max is equal to VQ. V is a shear force, VQ over IT. So the maximum allowable will be like last time we did a factor of safety of 1.5. You can still follow 1.5 as a factor of safety for the shear stress and also for the normal stress. Okay, you can use the factor of safety to be 1.5. Okay. Coming to the fasteners, adequacy of the fasteners. I will explain about this one in the next class while doing the calculation itself. I will explain how to determine the values of allowable and applied or the required values. Okay. That's one. The adequacy of fasteners used on built-up beams depends on the shear stress and the fasteners that can resist. Okay. In addition to the member property, the fasteners, whether it's welded or bolted, the bolts and fillets connected to the member will also have respond to the loading. That's what we did in the beginning of the class. like 2-3 classes before, we found the strain due to pin and the links and so on. Especially the required spacing of nails or bolts of a particular size is determined from the allowable shear force and shear flow, which is equal to VQ over I, calculated at points on the cross section where the fasteners are located. Right. That's why we need to determine, if you're asked to find out the shear stress, determine at the fasteners first and then for the whole member itself. Okay, you are asked to find out these three values, right? Maximum tensile, maximum compressive stress, and also radius curvature. For these two, you can use the formula, but you need to understand where the radius of curvature is lying. For this purpose, I have brought down here, and this one, no need, you already given. Centroidal distance is given to you, 38, and I value is also given to you. The strategy of getting the solution is write down all the formula that you are going to use. And this data already given. If not, you have to use this formula to find, right? But in this module, the whole module, I will provide you this data. You concentrate on others. Apply the elastic flexural formula to find the maximum tensile stress and compressive stress. So use this one. M is the maximum here. You can take it to be maximum. And then My also max. When I say this one is max, this is also max. Automatically, it will change to max. You can do it as a subscript. Okay. All right. And then because you need max, you need to substitute y max. Find out where is y max. Calculate the curvature using this. So I have given in the same equation. If you see the bending stress equation, you also have the R value, right? Same thing we can use here. It's a 4.9. Same equation. I just relate whatever the data I have. I need to calculate R. I have M. I have E. In the question, E is also given. E is given. So I try to use the relations that are given to me, right? A relation which has the data that is known, which is 1 over R equal to M over EI. These are the formula we are going to use. That's a strategy you're going to adapt. A concept you're going to, hypothesis you're going to adapt. Come on. Let's draw the diagrams. To avoid time, save time, I will draw before the class. This is a section. According to the bending, right? When it is the bending is causing like this, it will tend to bend like this. The deformation will take place like this. Unlike the last case, it will tend to bend like this because the bending is in this direction. If it is in this direction, it will go inside. This flange will go inside. When you draw the profile, the Y max will start from here, right? The maximum tensile stress, because the fiber has extended, right? So I will plot it as a tension here, maximum. Keep on reducing until the centroidal distance, centroidal axis. At centroid becomes 0. It's not to scale, it is very small, please understand. And then at central axis becomes 0. Then start the value of plotting the value of compression. It can even be like this in this direction, but direction of compression should be in opposite directions to show it is compression. You can even plot in this way, like the one in the video. Either this direction or this direction you can put. So the diagram of compression is in this way. From neutral axis, slowly increasing to the bottommost or extreme layer of the section. Okay, this is what the diagram shows. To find R, the location of the R, you mark on the center of gravity. Just complete the circle, the curvature. Then you can get the center. From the center to the fiber, then the end of this ring will be R. And you have A and B, where you can get your maximum values. This A to G, this section is perpendicular to the slide. Imagine this to be perpendicular slide. And the bottom one will give you the compression. Okay. See, this is the stress for compression and tension, compression. See the tension, you go and imagine, can you imagine the value? Tension is here, compression is here. Because Y is less, the value is also less. Y is more for compression, the value is also very high. See here, high. Then because Y is directly proportional to stress. So this is the value. You can yourself compare whether your answer is correct or not. Are you all getting this answer? Right? maximum tensile and compressive stress is got, and then finally the R value